Now, since this is a review video rather than a lesson video, I'm just going to focus on how to solve the problems rather than any kind of whys or logics to what we're doing. Here the leading coefficient is negative. Leading coefficient, the number in front of the highest degree term. That leading coefficient is -1, so that's negative. The leading coefficient determines the right end behavior. The leading coefficient's negative. You could say the right end behavior is down. You could use the word down. Or you could write it as x goes to infinity, because x is getting very large because that's the right end behavior. The outputs of the function, h of x, are going to -infinity. Next, we focus on degree. Degree is the highest power. Now, if the polynomial is in standard form, that's going to be the first term. You can see here, the leading coefficient is actually that one, because this isn't in standard form yet. So that would be the leading coefficient. So the degree is that highest power. So in this case, the degree, we could call that d if we wanted. The degree is 10. Now, 10 is an even number. If the degree, the highest power, is even, the left and right end behavior are the same. So if the right end behavior was down, the left end behavior would also be down and to the left. You could write it that way. You could write the word down. Or you could talk about as x goes to infinity, comma, h of x, or your teacher might write y, h of x would also be going to -infinity, just like it was at the right end. The degree is the highest power. The total number of roots. And remember, if a root or 0 was repeated 3 times, we're counting that 3 times. The degree is always the total number of roots. The maximum number of terns or extrema is always the degree minus 1. So 10 minus 1. The maximum number of terns or extrema would be 9. Now, this particular problem didn't ask you to write this in standard form, but we would just move the 5x cubed term to the second slot. But this is our leading coefficient. Leading coefficient is positive. So that means the right end behavior is up. Or we could write the word up. Or we could say as x goes to infinity, comma, c of x would also be going to infinity. Degree, again, is that highest power in the polynomial. So here, our degree is 7, which is an odd number. Degree is 7. Total number of roots is the same as the degree. And the maximum number of terns, or relative extrema, is the degree minus 1. So that'd be 6. When the degree is odd, the left and right end behavior are opposite. So if the right end behavior was up, the left end behavior would be down, or you could write the word down. Or, if your teacher prefers, you could talk about what happens as x goes to -infinity, way over on the left, comma, as x goes to -infinity, c of x would also go to not to infinity, it would go to -infinity. You can see those end behaviors are opposite. C and D are very similar. Now here, end behavior, we can just read it right off the graph. Here's our right end behavior. Here's our left end behavior. And imagine way down here past 5, if we continued forever, we'd approach an x of infinity. And if we went over to the left forever, we'd approach an x of -infinity. If we went up forever, we'd approach an f of x here. F of x would approach infinity. And if we went down forever, eventually we'd be looking at this. So based on the graph, we can say, I know it's kind of silly, but I'm going to start with the right end behavior just as a mnemonic device. Focus on right end behavior first, because that's what we did in A and B. The right end behavior, you could show up and to the right. You could use the word up, or if your teacher prefers, you could talk about as x goes to infinity, comma, f of x, because that's what our output function is here, f of x is clearly going to infinity as well. Whereas for our left end behavior, down and to the left, or the word down, or if your teacher prefers, as x goes to negative infinity, comma, f of x, see these are the outputs, f of x is also going to negative infinity. Next thing, when you have a 0 where you see this bounce behavior, the multiplicity of this 0 is a minimum of 2, and that's a minimum. It could also be 4 or 6 or 8. So for this one, we're actually going to talk about the degree. We're trying to come up with the minimum degree. Oh, and the end behavior is opposite, so we better come up with an odd number. This is one way to look at it. There's another way to look at it that we'll look at soon. So we got a minimum of 2. We got a multiplicity 1, multiplicity 1, multiplicity 1, 0. So these are all multiplicity 1. 1, 2, 3, 4, 5. So our minimum degree is 5. Now, our number of roots would also be 5. And this is a minimum. But it says unique and distinct. So the idea is we're not going to count this one twice. So it looks like we have 1, 2, 3, 4 unique or distinct roots. So notice those aren't the same. That's just based on the graph. Maximum number of turns or extrema, well, we can see that. We have the graph. So we're going to count the relative extrema, those points that are higher than those around them or lower than those around them. We have a peak, a relative max, a relative min, a relative max, a relative min. And what was the total number? It was 4. This one's a little bit different because this one, we could start with those number of relative extrema, 1, 2, 3. So really, it's not maximum number of turns or extrema. We see there's 3 of them. And remember that the number of turns or extrema is always going to be at most 1 less than the degree. So we could say, hey, minimum degree is probably 4, especially because we don't see any bounce behavior and we're not going to get anything else right now. End behavior, I'm not going to bother filling in here. We've done enough examples of that. You clearly have up, end behavior, and you could write those in any of the 3 formats that your teacher finds appropriate. Now, the number of unique or distinct roots, notice it doesn't say real roots. So maybe this is 4th degree with 2 real roots and 2 complex roots. In here, I'm not going to bother filling in the end behavior. You've had enough examples of that. Here we have a 0 that has multiplicity 2 or a larger even number, multiplicity 2 or a larger even number. So the minimum degree you could think of as 4. you can literally count the turning points, those relative extrema, relative max, relative min, relative max. There's 3 of them. And as drawn, the number of unique or distinct roots, there are 4 roots. There are at least 4 roots, but since we have repeated roots, we might talk about there just being 2 unique or distinct roots. This one gets a little more interesting because we have a clear inflection point. So that could be a 0 that's multiplicity 3 or a larger odd number. So that could be multiplicity 5, 7, etc. So when we're talking about degree here, we're talking about minimum degree. These clearly go through. So we got multiplicity 1 for those zeros. Multiplicity 1 for those zeros. No obvious complex zeros are jumping out at us in the graph. So 1, 2, 5, 6, 7, and the end behaviors are opposite, which it should be if the degree is odd. But this just as easily could be degree 9 or degree 11 or degree 13. Let's count up those turning points or relative extrema. 1, 2, 3, 4. This is not a relative extrema. This is an inflection point. Let's not talk about saddle points. Inflection point. This is a location where the graph changes from being concave up, cupped upward to concave down. But it didn't ask for inflection points here. So 1, 2, 3, 4. How about our distinct, unique distinct roots? 1, 2, 3, 4, 5. And make no mistake, the number of roots is 7. The number of roots, the minimum number of roots, I should say, the minimum degree is 7. And if the degree is 7, the number of roots is also 7. There's 5 unique roots, but one of those roots is repeated 3 times. It's called a multiple root. That root has multiplicity 3. Start off with C. Just because we have that beautiful symmetry across the y-axis, which is what we're looking for an even function, justification, graph is symmetric across y-axis. Now to be odd, we need to be symmetric about the origin. That's what we have here. See the over 2 up 1, over 2 down 1. We would say the graph is symmetric about the origin, or with respect to the origin. Now, depending who printed your review for you, your version might have perfect symmetry across the y-axis, but this one does not. See how it's just a little bit off? It's not quite symmetric. Well, not good enough. That's neither. Graph is neither symmetric across y-axis. Neither goes with nor symmetric about the origin. Close, but not quite symmetric across the y-axis. Now for this page, the justification statements are going to be the same as the previous page. Hey, that looks about perfect. It looks like we have that nice symmetry across the y-axis, which means we're even. Justification graph is symmetric across or about across the y-axis. See that over 2 or over 1.5 down. We have that nice. It's like this part of the graph. To get the other part, you'd reflect across the y-axis and then reflect across the x-axis. You get that double reflection action. That's odd. Graph is symmetric about the origin. And finally, here clearly neither of those things are true. Graph is neither symmetric across y-axis nor symmetric about the origin. So here we're asked to determine algebraically whether these functions are even or odd or neither. So we begin by composing. With an input of negative x instead of x. And we see if this simplifies to the original function, we're even. If this simplifies to the opposite of the original function, we're odd. And if neither are true, it's neither even nor odd. Negative squared, so negative x times negative x, that'd be positive x squared, which is the original function. So we've shown f of negative x is f of x. Therefore, f is even. There are shortcuts you can use to determine even and odd, but that's not what it asks you for here. It asks you to determine algebraically whether the function's odd, even, or neither. So again, we begin by replacing every x with a negative x. So we're finding g of negative x. Negative to an even power is going to come out positive, so this simplifies to 14x to the fourth minus 3x. Now, is this the original function? No. Is this the opposite? The opposite of the original function would be the opposite of each of these terms, so that'd be negative 14x to the fourth minus 3x. And this is not that. This is not the original. So you could say g is neither even nor odd. Could circle neither, whereas over here we would have circled even. Now, if you wanted to show additional explanation, this really covers it, but you could actually say g of negative x was not equal to the original function, and g of negative x was also not equal to the opposite of the original function. These two statements is actually the mathematical justification for why g is neither even nor odd. If this was equal, you'd have g be an even function. If this was equal, g would be an odd function. Again, we begin by finding g of negative x. How do we do that? We substitute negative x here and here. Negative to an odd power, that'd be negative times negative times negative. That would come out negative. Negative times negative is positive. Now, depending who your teacher is, they might have showed it one way, they might have shown it another. Now, clearly, this is not the original function, so we're not working with an even function. So the next thing we could do is factor out a -1. Hey, look, what's that? What's this blue stuff right here? That's the original function. You have shown that h of -x is the opposite of h of x. That is the mathematical definition of an even function. Therefore, this just means therefore, triple dot, h is odd. Circle done. The other way to look at this is to stop here. You could have also done this by looking at the opposite of h of x. So that's the opposite of h of x. So you're going to reverse the sign on each term, because you'd just be multiplying h by -1. So you'd get -6x cubed plus 8x right there. So you could also say, oh, negative h of x is the same as this if you wanted to. Now, as soon as you see odd powers and even powers, you know this isn't going to be even or odd. We already know it's going to be neither, but we still want to determine that algebraically. So m of -x, always the same starting point. Replace every x with a -x and see what happens. Negative to an odd power is going to come out negative. Negative to an even power is going to come out positive, but then we still have this negative. Is that the original function? No. Is this the opposite of the original function? No, because see, that's the opposite of the first term, but not the opposite of the second term. So as soon as you get here, if you wanted to, you could say, therefore, m is neither even nor odd. Now, what else could we put here if we wanted to? It's clear that m of -x is not equal to the original. We can also say m of -x is not the opposite of the original. Just didn't happen. Now, what is the opposite of the original in this case? The opposite of m. You'd reverse the sign in every term. -4x cubed plus 2x squared minus 15. See, they don't match. So it's neither m of -x is neither equal to m of x, nor is m of -x equal to negative m of x. So m is neither even nor odd. I don't really think we need to work through E and F. More of the same. Are each of these polynomials in standard form? Highest degree term first, lower degree, lower degree, lower degree. Yep, they're all in standard form. So end behavior is always going to be determined entirely by the leading term in standard form. Right end behavior, right end behavior, right end behavior, right end behavior is always determined by the sign of the leading coefficient. The leading coefficient is -3, so the leading coefficient is negative. That means your right end behavior is down, or you could use the words down. Or if your teacher prefers, you can write as x goes to infinity, comma, g of x goes down, so goes to -infinity. Next, the highest power is the degree. Here, the degree is 2, which is an even number. If your degree is even, your left and right end behavior are the same. So it'd be down and to the left, or the word down. Or if your teacher prefers, as x goes to infinity, comma, g of x goes down, so goes to -infinity as well. And again, even, degree, end behavior is the same. Here, the leading coefficient is 5, which is clearly a positive number. So as x gets very large, this gets very large and positive. P gets large and positive is one way to think about it. So as we go to the right, we go up, or you could write the word up. Or if your teacher prefers, you could write as x goes to infinity, comma, p of x also goes to infinity. Here, the degree, the highest power, is 3, which is an odd number. When the degree is odd, the end behaviors are opposite. So if the right end behavior was up, always start with the right end behavior. If the right end behavior was up, the left end behavior would be down. Or you could write the word down. Or if your teacher prefers, you could say as x goes to negative infinity. Oh, whoops, I needed to make that a negative infinity. That needed to be a negative infinity. As x goes to negative infinity, p of x goes to negative infinity, because the outputs are decreasing at that down end behavior. Here, our leading coefficient is positive. That means our right end behavior is up. Or you could write the word up. Or you could write as x goes to infinity, h of x also goes to infinity if your teacher prefers. The degree is 4, which is an even number. If the degree is even, the end behaviors are the same. So if the right end behavior was up, so too will the left end behavior. It'll be up. Or if your teacher prefers, as x goes to negative infinity, let's make sure I don't make the same mistake I did up there. As x goes to negative infinity, h of x goes to infinity. Degree is even, end behaviors are the same. Up, up. I think we've done enough of these. I don't think we really need to do D. First, we need to review transformations a little bit. It doesn't really matter that f of x equals x to the fourth. All that matters is that g is a transformation of f. So general transformation format. F of you can use a lot of different letters for this, but I'm going to use A. If A is negative, we get a reflection across the x-axis. If A has an absolute value larger than 1, we get a vertical stretch. If A has an absolute value between 0 and 1, we get a vertical compression. So there's a lot of information that can be contained in whatever the coefficient is here. This is the sneaky one. You have to factor out the b and make this just an x minus h plus k. So h comma k covers your horizontal translation, whereas k is going to cover your vertical translation. And your teacher might say shift. Vertical shift is fine as well. Horizontal shift. A covers some different things. If A is less than 0, you have a reflection across x-axis. If the absolute value of A is greater than 1, you have a vertical stretch. You could talk about with a scale factor of absolute value A. If absolute value A is between 0 and 1, we have a vertical compression. And again, we could talk about with a scale factor of whatever the absolute value of A is. B is similar, and man, they snuck B in here. We do have those B situations. It's going to be very similar to this, but we're going to talk about horizontal compressions and stretches and reflections across the y-axis. If b is less than 0, we have a reflection across y-axis. If the absolute value of b is greater than 1, we have a horizontal compression. Now we're going to add the scale factor part in. Your horizontal compression with a scale factor of 1 divided by the absolute value of b. Whereas here, if the absolute value a greater than 1, this is our scale factor. The absolute value of a is the scale factor. So this is a vertical stretch with a scale factor of absolute value a. And this is vertical compression with a scale factor of absolute value a. There's slightly different terminology your teacher could use here if they wanted to. Now, if the absolute value of b is between 0 and 1, we have horizontal stretch with a scale factor of 1 over the absolute value of b. There's a lot of information there. So this is just a quick review of transformations. Now we can take a look at these specific problems, see if we have enough room here. Maybe I'll zoom out a little bit. Bet you didn't think that was a turtle foot on a giant pot holder. It's to keep the camera from vibrating too much. I probably should invest in some weights or a proper camera mount, but it'll work for now. So you're almost ready to talk about, oh, here we have a vertical compression. Here we have a reflection across the x-axis, but see this 4x plus 7 part? You have to factor the 4 out. You have to factor the half out. And then we can talk about all our transformations in precise terms. So this would be 4. And see, we factored a 4 out, so it'd be x plus, divide that. When you factor, you're really dividing. So divide 7 by 4, that's 7/4. Because see, if you distributed, you'd get back to 7. Here, we're going to factor out a 1/2. So divide by 1/2. What is 6 divided by a half? That's a 12. Oh, and then we're going to have a nice, boring vertical shift down 8. So now we're going to use all this information for this. So I'm going to pull this away. And you can always refer back to it. Now, if your teacher wants you to be really precise, you can talk about what the order the transformations are in. I don't think they really want that. I think they just want to describe all your transformations. I kind of like to start on the inside and work my way outside. So first, we have a shift 7/4 to the left, because see, this is a plus 7/4. So this is a shift 7/4 to the left. Now this, remember, this, that's a 4. That's actually a horizontal compression with a scale factor not of 4 but of 1/4. We have a horizontal compression with a scale factor of 1 divided by the absolute value of that, so a scale factor of 1/4. And then we also have a vertical compression. We have a vertical compression. And when you graph things like this in Desmos, which some of you might, because see, Desmos will work with composition notation. Well, it doesn't work perfect, but it's pretty good. You could put f of x in, and you could put g in like this. It's going to be hard to tell the difference between horizontal and vertical compressions and stretches because they kind of have a combined graphical effect for some functions, especially polynomials. So this is vertical compression. You could say by a factor of 2/3 or with a scale factor of. You also could use whatever verbiage your geometry teacher taught you. Moving over to this one. Again, we have a shift to the left. So 12 to the left, shift, 12 to the left. I'll also talk about translation. Now this is a 1/2. So that's a horizontal stretch. So we have a horizontal stretch with horizontal stretch with a scale factor of 1 divided by 1/2. 1 divided by 1/2 is 2, or the reciprocal of 1/2, a scale factor of 2. Then what's the minus sign do? We have a reflection across the x-axis. And then finally we have a shift 8 down. And these are written consistent with. This is the part you want it committed to memory. This is a test they often don't give you a note page on. Now, one of the reasons why is you've been working with all of these transformations in prior units, except maybe this capital B, the reflections across y-axis, horizontal compression, horizontal stretch. Way back in geometry class, they probably had you work with transformations. And it might have been an original coordinate x comma y was mapped after a transformation to a new coordinate. Now you can see here, this is what we looked at in number 5, and if you want a more thorough explanation of this, go back to number 5. See the +1, that's going to increase y by 1. We're going to have that vertical translation or shift. What's this 5 going to do? It's going to multiply the output of the function by 5. So it's going to multiply the output by 5. So whatever our original y was, we'll come back to the x's in a second. Whatever the original y was, we're going to multiply that by 5 and add 1. Now, what happened to this poor x? Well, what does this minus sign represent? That represents a reflection across the y-axis. And think about it. If you were over here, if you reflected across the y-axis, you end up with the opposite x value. So what's going to happen here? We're going to get the opposite of the x value. But I'm going to leave a suspicious gap here. But what does this 2 represent? It represents a horizontal compression with a scale factor of 1/2. And if you compress, see, you'd move towards, you'd be getting smaller. So this is actually, right here, we need that 1/2. Once you have your mappings set up, your transformation written in this way, it'll be really easy to transform each coordinate. So over on this one again, we had x comma y is going to map to x comma y on this f graph is going to map to a corresponding point on the g graph. This is a shift 3 to the left. This is a shift 6 down. And this is a vertical compression with a scale factor of 1/2. So you're chopping those y values in half and then moving that y value down 6. So our x, this is 3 to the left. So x gets moved 3 to the left, has its x-coordinate reduced by 3. Then what happens to our y? It gets cut in half and then reduced by 6, representing that shift, 6 downward. And we can take this away. So if the original coordinate was 0, 0, the corresponding point on the other graph, 0 minus 3, is negative 3, comma, 1/2 times 0 minus 6, which makes so much sense. Doesn't matter what this function was. Wherever this thing's inflection point was, this had an inflection point at 0, 0. This graph's corresponding inflection point would be negative 3, negative 6. Here, original 1, 1, so 1 minus 3 is negative 2, comma. 1/2 of 1 is 1/2. 0.5 minus 6 is negative 5.5. And you, of course, could use a calculator if you wanted. Negative 1 minus 3 is negative 4. There's a lot of different ways you could do this. 1/2 times negative 1 is negative 1/2. Minus 6 is negative 6.5. 2 minus 3 is negative 1. 1/2 of 8 is 4. 4 minus 6 is negative 2. Negative 2, x is negative 2. This is my x and y. And then my new corresponding point, this is going to be x minus 3, and this is going to be 1/2 y minus 6. So negative 2 minus 3 is negative 5. 1/2 of negative 8 is negative 4. Negative 4 minus 6 is negative 10. And of course, you could use a calculator for this if you wanted. Now, back when we graphed quadratic functions, often you were asked to graph 5 points, including the vertex. For cubic functions, often you're asked to graph at least 3 points, including the inflection point. But other than that, you could graph using transformations, or you could graph using XY tables, as long as you can identify the inflection point. Now, before we sketch these, let's talk about the parent function. So y equals x cubed. Let's do a 1-to-1 scale. What's y equals x cubed look like? 0 cubed is 0. 1 cubed is 1. 2 cubed is 1, 2, 3, 4, 5, 6, 7, 8. Negative 1 cubed is negative 1. Negative 2 cubed is negative 1. Negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. Cupped upward, concave up. Cupped downward, concave down. And this right here is called the inflection point. The inflection point in this case would be the origin. So then when we move into transformations, we're talking y equals a b x minus h cubed plus k. You could also call this c and d, depends on the teacher. I like this version because then we can talk about, oh, h comma k is the inflection point. And it's not that bad. And if you can identify the inflection point, in this case it'd be 3, 1, you could always graph 3 points using an XY table. So here, our h comma k, our inflection point, is clearly 3, 1. So we could always graph that first. 3, 1. Shortcut, if your a is negative 2 and there's no horizontal compression or stretch, we don't have that situation. The negative 2 instead of going over 1 up 1 from the inflection point, you're going to go over 1 down 2, over 1 up 2. That's all. And then you can sketch your concave down, concave up, because we want that inflection point behavior. It's not great, but it's good enough for a test where you want to show the inflection point and at least 2 other points. And it's going to be hard to get the next point anyway if this is a 1-to-1 scale, because see how this is over 1, up 1, over 2, up 8? It's over 3. 3 cubed is 27. You're going to be off the grid. This is good enough. Another way to look at this. Remember, this is an x and a y. If we know 3, 1 is our important point, our inflection point, 3, 1, and see there's no horizontal compression or stretch, we probably need this coordinate and this coordinate. And you could obviously evaluate the function at those 2 locations, and guess what you'll get? You'll get this point and this point. And you could go farther if you wanted, but then you'd have to change the scale. This is test review, so let's keep it simple. Either use this method or use the shortcut method if you don't have a horizontal compression or stretch, which we probably will somewhere in this review or maybe on the test. But there's even a way around that, and I'll show you that when we get to that problem. Problem 8 is more of the same, but if we were going to go ultra shortcut method, it'd be h comma k is -4, 4 to the left, and 3 down. And we graph that first. So 1, 2, 3, 4. That's -4. 1, 2, 3, -3. Always got to show at least one value on each axis for scale. So here is our inflection point. We have this vertical compression by a factor of 1/2. So instead of over 1 up 1 like we have on the parent function, it's over 1 up 1/2, over 1 down 1/2. Now here we could squeeze another point in, and let's just do it. It's not required. If it was a test that said show the inflection point and 2 other points, so showing at least 3 points. But think about how 2 cubed is 8, so it's from the inflection point over 2 up 8. We'd instead from the inflection point be going over 2 up 1/2 of 8 is 4. 1, 2, 3, 4, so we'd end up here. Over 2 down 4. 1, 2, 3, 4. Concave up, concave down, and we have that nice inflection point behavior right there. This is H. This is F. But this might be the most important. This is y equals x cubed, the parent function. Now, you go, dang it, there's a 2. That means we're going to have some sort of horizontal compression just to make things complicated. No, you don't have to do it that style if you don't want to. See how this is 2x cubed? 2x times 2x times 2x would be 8x cubed. What's 1/2 of 8? That's 4x cubed plus 2. So you don't have any kind of horizontal shift. So what is the location of our inflection point, h comma k? You wonder what I'm talking about. Here's our parent function. Here's our transformed function right here, 4x cubed plus 2. Oh, so we don't have any horizontal shift, so the inflection point is going to be at 0, 2. And we have a vertical stretch with a scale factor of 4. So instead of starting at 0, 0 like with the parent function here, we're going to start at 0, 2. Instead of over 1 up 1, we're going to have over 1 up 1, 2, 3, 4. And you can always check. You could make an xy table with the original function and, of course, use -1, x equals -1, x equals 0, and x equals 1. substitute in and make sure you get the points that you see on your graph. This is usually not a test where students are particularly rushed. And then over here, we're going to have down 4. 1, 2, 3, 4. Cupped upward, concave up, cupped downward, concave down. Label at least one value on each axis for scale. And we could label this -2 if we wanted to, but we don't have to. And this is just going to be more of the same. If you go back to 7 through 9, I covered, or at least alluded to, why we don't need a b here when we're trying to find the equation for a graphed cubic function. It could be a 5th degree, it could be a 7th degree, but it says state the equation with the lowest degree for the graphed polynomial. So let's just pretend this was a cubic. Our inflection point, our h comma k, looks to be 1, 2, 3, 4, -3. So we already have h and k. And we also have another coordinate. And this appears to be 5, -5. So we know h and k, we just need to know a. So we substitute h and k in, and then we substitute in the other coordinate for x and y. We solve for capital A, and then at the very end, we write our final equation and box it and call it a day. And then we can always check if this is the correct equation by substituting in x equals 4 and x equals 5 and make sure we get the correct y values of -3 and -5. Okay, so we got our h and k. We're going to substitute those in. We're going to substitute in our x and y as well. So y is -5. And yes, there's another shortcut way to do this, and I'll cover the shortcut in a moment. Our x is 5. Our h is a 4, so this is -4 cubed, and our k is a -3. 5 minus 4 is 1, so there's a. Just add 3 to both sides. A is -2, so now we can write the full equation. -2, x minus h, x minus 4, cubed minus 3. Which really fits the graph, because we have an inflection point at 4, -3. You also can think of as transformation, shift 4 to the right, shift 3 down, as compared to the parent function y equals x cubed. And instead of over 1 up 1 like with the parent function, we have over 1 down 2, down 2. That's the shortcut. If the second point is 1 unit to the right, you can just read the a value off. What if it was 1 to the left? Well, there is one right there. See how that one's right at a grid mark? But just focus to the right. Always to the right. Over 1, down 2. Okay, your a value is -2. Oh, see how they give you choices here? And what's funny is you could use that one. We go, is that at a half? Probably. You could also use this one. You could also use this one. Any of those ones will work. Now, is it -1, 2, 3, 4, 5, 2? So your inflection point is -5, 2. That's the most important point. Your h, k is -5, 2. What do you want to use as your second point? Do you want to work with fractions or do you want to not work with fractions? It's your choice. I'm going to work with -3, 1, 2, 3, 4, 5, 6. You also could read the a value off. A is 1/2. See, over 1, up 1/2, a is 1/2. If you ever have a second point that's 1 to the right of the inflection point for a cubic function, a over 1, up 1/2 would mean a is 1/2. Well, let's do the more formal method. We have our x comma y, negative 3 comma 6. That's our x and y. We have our h and k. We can substitute in our y and our h and our k and solve for a. And then at the very end, we'll go back and write what the equation is, even though we could use a shortcut and get it immediately. We don't know a. X is negative 3. Whoops. Y is 6. Minus h, so that'd be plus 5. Cubed plus 2. 5 minus 3 is 2. 2 cubed is 8, so 8a plus 2. Minus 2 minus 2. And look, we get exactly what we knew we would get. We knew a was going to be 1/2. We knew it. So a is 1/2. X minus h, so plus 5. Plus 2. Inflection point, negative 5, 2, right there. A is 1/2, so over 1 up 1/2. No work is required for this. You can go directly from the graph to this if you have that coordinate 1 unit over, 1 unit to the right from the inflection point. I think that's enough of these. Over 1, down 1, 2, 3, 4. A is negative 4. Okay, here we're going to write a cubic equation in standard form with these roots. And just think, it's cubic, so we're going to write it like f of x equals, you got some choice here, and I'll come back to this in a moment. You have the option of putting an a here, and we'll have the first root, and the second root, and the third root, exactly 3 roots because we're working with a cubic function. And it said standard form, so we're going to expand this completely. And there's shortcuts you can use for the expansion, but it's not really required. Now you also know that if 2i is a root, so too is negative 2i. If 2i is a root, so too is negative 2i. So if we're going to write this, minus 3 is a root, so we'd have a minus 3, so we'd have x plus 3. And let's just make it 1 here. So it says write a, it doesn't say write all of the. We're just making a 1. Going to make the leading coefficient 1. So we're going to have x minus 2i, x plus 2i. And hey, if you know any of the expansion shortcuts, or even want to use that British tinged version I showed, you could, but you don't have to. You could just patiently distribute because it's something you should be comfortable doing by now. X times x is x squared. X times 2i minus 2i times x, those two terms are going to cancel out. Because you'd have 2ix minus 2ix. And then finally, negative times positive is negative. 2 times I is 4i squared. And you can skip this step because you're supposed to know, oh yeah, I squared, that's always just negative 1. So this is really x plus 3 times x squared plus 4. One of the weird shortcuts to come up with this. Oh, these roots are plus or minus 2i, so you could say x is plus or minus 2i. Square both sides. X squared. Positive squared, negative squared, plus or minus squared is just going to be positive. So you'd get 4i squared, which is 4 times negative 1, which is negative 4. X squared plus 4 is 0. So this x equals plus or minus 2i is equivalent to this, so then that would become a factor. Don't have to do it this way. And there's other things you could do. But we're not done yet. We need standard form. So you have to distribute again. And then reorder the terms so they're in increasing order, or decreasing order of power. So x times x squared is x cubed plus 4x. You know what? I'm going to put that here because I know I'm going to get a 3x squared, and a 3 times 4 is 12. And if you have extra time to check your answers, you always could make a table or graph for this and compare it to this. Some of the calculators will actually even graph with the imaginaries, but it depends which calculator you have. Now, B is only slightly different. So this was A. I just want to comment on what's different on B. And again, you have choices. Don't even have to call it f of x. You could call it y. Now, you could write this. I'm going to cross this off for a second. You could write this as x minus 1/2, but then you're going to have to work with fractions, and a lot of kids don't like to work with fractions. Instead, see, I said f of x. No, not equal. This would be a cubic function with these zeros. But you could also multiply by 2, and make this 2x minus 1. Because see, still, this, if you set this equal to 0, you'd get x equals 1/2. If you set this factor equal to 0. Other than that, you're just going to distribute. It's going to be the same process. You can use this shortcut or some other shortcut if you wanted to. But the method is going to be the same on all these.